on behalf of my co-authors, a couple of whom are in the audience, Schneider and Karon MacLean up here in the front. And so the SPIN lab, SPIN stands for sensory, perception, and interaction. And what we do is that we're a haptics lab. And that means that we take a look at the sense of touch, and specifically the sense of touch and how it can convey emotion. And we do this using a bunch of different little fun devices, for example, like haptic paddles or knobs, or the stuff that we'll be talking about today, robots. And specifically kind of fun little simple furry robots. So the name CuddleBit, I'll tell you a little bit where the name CuddleBit comes from. And the best way to talk about it is to tell the story of a CuddleBot. And so a long time ago, we asked the question of how does affective touch work? And if you think about it, it's kind of a difficult thing to study, right? If you imagine, you can't really talk to, let's say, a dog that easily. And so if you build a robot, maybe you can take a look at the way that people do emotional touch interaction a little more closely. So we developed a cuddle robot. We developed a touch robot, a haptic creature, and discovered that it was good for cuddling, which I guess kind of makes sense. If you got a soft, furry robot, you might want to cuddle it. And so a CuddleBot can be good for a lot of different things. It could be a pet. And you can imagine maybe it's like a classroom pet, and maybe the kids are like playing with it and learning about robotics. Or maybe it's like a family pet, and everybody's being entertained by it. Or maybe it's like a therapy animal, and you tell it an emotional story, and you touch it and you feel better, right? Or you can do what we do with it, and we use it as a study tool to look at affective touch. Okay, so we built a few of these things, and it's kind of tough. It's kind of tough to build robots, right? I'm not sure how many of you people build robots. Looks like a few of you, but it's a tough thing. So here's a picture of our first one, and you can kind of see, it's not that expressive of a robot. Kind of on the back here. Let's see if this works. Oh yeah, there it is. That's the thing that kind of made it breathe, and that doesn't really look like breathing that much, right? And then it's got some inflatable ears here, and they weren't as expressive as we wanted them to be. And so here's just kind of a picture of the inside mechanics, and then a more recent CuddleBot. And so we engaged a engineering firm to do this, and they went through a traditional sort of engineering process where they worried a lot about, where do the motors go, what kind of materials are we using, what are the power requirements? And kind of taking this engineering perspective, we found doesn't really get at that core question of expressivity. That's really what we're trying to get out of these robots, right? If we're going to do these touch interactions, we need them to be expressive. And so we need to redesign this robot again. And so we really need to focus on this idea of making something expressive requires some kind of improvisation, right? You need to be able to sort of sketch something to get at that more expressive aspect. So that's kind of what I'm going to be talking about today, is how we can get at sketching robot form factors. And so I'll tell you about the two robot systems that we created, and I really want you to focus on this idea of designing for redesign, this idea of sketching and improvisation. Then I'm going to tell you about the behaviors we designed for the robots, and then how we went about evaluating them for their emotional content. Then I'll tell you a little bit about how we took a look at the waveforms that produce the behaviors and looked at the features that features that you can take from those waveforms and how they map onto the dimensions of arousal and valence. So finally, what are CuddleBits? Well, CuddleBits are the answer to the CuddleBot. They're easy to design, they're cheap, and they're fast to iterate on. And when we say cheap, we mean like, in the tens of dollars. Fast to iterate on, we mean, in the minutes to hours to rebuild. We achieve this by focusing just on a really simple expressive aspect of it, and it took a lot of work to sort of make them fast and cheap. And so the real research question that we're getting at here is like, how expressive can we get with just this 1 degree of freedom breathing behaviors? And we looked at breathing behaviors because that's a very emotionally salient thing we found with the CuddleBot. We found that it actually calms people down. You can take a look at this, and their physiology actually changes as a result of these breathing behaviors. So it's a lot of fun. And so if we're going to be designing these robots for expressivity, how do we have to rethink our robot design process, right? And so we're sort of throwing away all these engineering problems, or at least pushing them to the end, and treating it more like an art problem. than an engineering problem. And so I'll use the analogy of a puppet here. Thinking about designing a puppet, you don't design it the same way you design a robot. You're not sitting there with like, AutoCAD or like SolidWorks or something like that and really doing all the drawings for this thing first. You're sort of designing it by hand as you go along. Right? And so the real key thing here is that if you want to improvise, if you want to change the expressivity of this puppet, you can just like do that. You just change the prototype immediately. And that's the kind of stuff we want to support with the CuddleBits. So I'll just play these little videos of our prototyping process. And we start off real simple, kind of taking that classic HCI route of paper prototyping and other kind of low cost and low fidelity kind of prototyping. And what's really fun about it is, you can get sort of a new robot prototype really just in minutes. I can sit there with a knife, a mat board, and a hot glue gun and lay a little bit of fabric over top and okay, we've got a new robot prototype. And so after going through just many iterations of these robots and exploring a bunch of different actuation mechanisms, we found a couple of streams started to emerge. And so eventually we started getting this one more rigid robot. This one's made out of wood. We call it the rib bit because it kind of looks like, an actuated set of ribs. And then we also started, we converged on this thing called the FlexiBit, named as such because the structural components are flexible. I'm really proud of this one because it's basically just made out of a binder. I think that's a lot of fun. Yeah, and so as often happens when you go through the design process, you make a lot of iterations of something, you start being able to see the commonalities between them, right? And we realize that we're not just sort of like designing individual robots as much as we're designing systems of robots. And so we'll talk about this idea of a design system here. So a design system is composed of modular, reusable, and easily modifiable elements. And so I want you to think of like a brand you might develop as a graphic designer for a company, right? You don't just sort of make a business card. You make maybe a logo, and you also make a color scheme and maybe some canonical shapes. And then you mix and match those things to produce, sure, a business card, but also like a website and like a mobile app or something like that. And so that's the kind of idea that we're trying to get at here with these CuddleBits as well. We're trying to find these design systems so that we can produce a lot of different CuddleBits and not just do one robot, but do a whole family of robots, right? And so here's the FlexiBits design system. It's just made out of slices and bases. And so the slices are the flexible parts that go on top. The bases where you're going to stick the motors. And the really fun thing is that you can take it into some kind of really simple design program that almost anybody has, like Sketch or Illustrator, and just change the size of the slices and get a whole new robot form immediately. Here's the same thing with the rib bit. Here's the rib bits design system, and it's very simple again. Basically just some ribs and some things to hold up the ribs. And if you want to maybe get a little bit more texture out of those ribs, you can take that into Adobe Illustrator or Sketch or something like that. Draw a few circles on the ribs and send that to your laser cutter. Get a new robot in a few minutes. Okay, so now that you've got the form factors, you want to design behaviors for this. Although I'd like to stress that this is not something you can really do linearly like that. You sort of have to design these things together, right? The way that the robot is shaped obviously, sort of determines how the robot's going to move. And so we really wanted to take this idea of improvisation into the behavior design as well as the form factor design. And so we tried a lot of different kinds of sketching methods. And so we thought about, okay, what if we can sketch a behavior with your hand? Or maybe what we can do is like turn a knob or something like that to make the robot move. But we found that human hands didn't quite get at what we wanted. It wasn't quite expressive enough. And so Oliver had the amazing idea of, what if you could express haptics through your voice? Because that's a really sort of like natural way to express motion, right? If you kind of think you go like whoop, 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 that's sort of like oscillation, right? Or if you go like whoosh, right? That's sort of like really fast movement. And so we built a system that does that. And so I'm just going to play this video here, and I want you to listen to this lady. Oh, yeah. So she's just barking into a microphone and the robot's responding. And, that's a lot of fun. and so all this does, it just maps pitch and amplitude to robot pose, right? And I think that the really key thing here to look at is that, so it picks up the big barks, right? And they get big robot motions there, but it also picks up sort of the light inhalations And then you kind of get the robot fluttering. And the thing to point out here is that this is a thing that's really tough to design for, right? You can't just sort of get that sort of expressivity, or you can. It just takes a lot of work to get that kind of expressivity out of an animation, right? And so allowing people to do this kind of improvisation gets at this sort of like spark of life of the robot and gives this real sort of naturalistic feeling. Okay, so once you've designed this behavior with your sketching tool, you probably want to make some modifications to it and refine it. And so we also developed a keyframe editor built off of some other work by Oliver. And what you'll do with this is maybe you want to copy and paste different parts of the behavior you just sketched. Maybe you want to add a little bit of roughness here and there or smooth some parts out. Okay, so now you've got a behavior that's designed. That's very good. You want to figure out whether it does the thing you expect it to. And so we went about this in a lot of different ways. I'm just going to talk about one way, but you should check out the paper for the other ways we went about this. And what we did is we gave participants, 10 people, emotion words from the positive and negative affect schedule, or the PANAS. And I'll just explain what that means. And so basically what the PANAS is a list of words from psychology that's been mapped to different quadrants in the affect grid. And what the affect grid is a two-dimensional model of emotion where you've got arousal or activation on one dimension, and then you've got valence or pleasantness or unpleasantness on the other dimension. So let's just take a look at stressed. So you can imagine stressed, you're fairly highly activated, but it's an unpleasant thing, right? And so we'll call that high arousal, low valence. Versus excited, where you're still fairly highly activated, but it's a good thing, right? It's a pleasant thing. And so we'll call that high arousal, high valence. Okay, so then we grabbed a few of our design behaviors and then a whole new set of people. And what we did is we showed these behaviors to these new people. And we had them rate the behaviors. And so the way that you do that is we got them to choose the top 3 words from the PANAS that represented the behavior and then indicate the strength that each behavior represented the word. And so this animation just kind of goes through that. And then what we did is that we just sort of combined the different weightings to get a single point on the affect grid. And the reason why we did this is that we thought that allowing people to look at 3 different words for the same behavior would get at more of a true representation of what that emotion might be than maybe just a one-off shot, right? Okay, so eventually we create 1 point per participant per behavior, and we're able to aggregate them and do a little bit of analysis, right? And so the important thing was to see how consistently these behaviors were perceived by our participants. And so what you're seeing up here is a whole bunch of different ratings, and you'll see that they're all in this top left quadrant of the affect grid. And around it, you'll see a confidence interval of 5% and a outer confidence interval of 97.5% and a mean and a median. And so the mean and the median are important, but not that important. The important thing is to look at these confidence intervals and really figure out what the spread of the data is. And so we can say here with this behavior that we've called scared, that it's fairly consistently something that's highly activated, as you might expect scared to be, and low valence, right? So fairly unpleasant. Okay, so that's one pattern that we found in our data. Another pattern that we found is where the behavior was clustered along one dimension but not along the other. And so here with this behavior that we call determined, we're seeing that it's a fairly highly activated, fairly highly aroused behavior, but it's not particularly well validated in terms of valence, right? So this could be perceived as positive or negative. And then the third pattern we found is, who knows, right? And so the important thing to look is the mean and the median here sort of seem like where you might place drowsy, but the spread is so wild that we couldn't call this thing validated in any way. And so we did this for a whole bunch of different behaviors, and they're all in the paper, and there's a bunch cut off at the bottom there. I encourage you to take a look. Okay, and so the last thing that we did is that we took those behaviors and we extracted some statistical features, such as the variance along the behavior or the maximum, right? So how big the robot gets, or the minimum, how compressed the robot gets, and then we correlated these with the emotional dimensions of arousal and valence. Right? And so what we found was that bigger and faster motions contribute to arousal. And so this kind of makes sense, okay, here's regular breathing, right? And then right, that's a little more highly aroused. And then we also found that higher complexity of motion, and complexity is defined in a lot of different ways, you should check it out in the paper, contributes to valence. And this kind of makes sense. Again, regular breathing is like, but then like, that's a little bit, more unpleasant. All right, so those are our correlations. Okay, so I'll just summarize and tell you where we're going next. I got to play these guys. There we go. Okay, so we developed 2 robot design systems, and specifically they were designed for redesign. So what we want to do now that we've done this breathing behavior stuff, we want to look at other degrees of freedom, right? So like if you kind of think about, what about ears or like head motion or spine motion? Then the next question is, once you've designed behaviors for that using the same system, how do those degrees of freedom work together, right? Is spine motion like more interesting than breathing motion? Who knows, right? Maybe it's more emotionally salient, maybe it's not. So that's a really interesting thing to look at. And then last is how do these, once we're able to correlate behavior features with the valence arousal, right, make some kind of mapping between a feature of a behavior and valence and arousal, then we don't have to rely so much on just designing these behaviors and maybe like replaying the same robot behavior over and over again and getting boring during an interaction. But what we could do is maybe generate them and say something like, okay, get to this point on the affect grid and do some kind of representative behavior for that. So that's where we're trying to go. And last, I'll just point out, if you want to go to cs.ubc.ca/lab/spin/CuddleBit, we have our project page up there, and we also have our templates and some instructions for creating your own. So I'd love to see all of you make your own little CuddleBits and play with them at home. So thanks again, and thanks to everybody who worked on this paper with me. Questions? I was hoping that same guy would show up.
Anyone has questions?
Hi, I'm Amanda Jung from the University of Rochester and also the Rochester Institute of Technology.
Right.
I really like the voice aspect of controlling the behavior. I was wondering if you also considered facial expressions?
Oh, fun, yeah. Okay, so no, we just did the voice thing, and actually we got a whole paper on that. You should check out at DIS. Facial expressions we did not do, and I hadn't even thought about that. Yeah, so you kind of want to do that live, eh?
Right, because I was also thinking of, with like interacting with babies, you have motherese with the voice, but you also have huge facial expressions.
Yeah.
As well.
So yeah, I think that's a really interesting point, right? Because there's a certain amount of like expressivity that you got to put into facial expressions, and sometimes it's a little bit difficult to tell what people's facial expressions are. And what you actually kind of need to do is make some kind of live acting system. And I think we did that with the vocal input thing, but it'd be awesome to do also like pose tracking of some sort, and facial tracking would be excellent. Like it would give it a nice nuance. Okay, thanks.
Fraser Anderson, Autodesk Research. Very cool work. I was wondering, at the start you sort of contrasted this with the formal engineering approach.
Yeah.
I'm wondering if you guys have considered the artistic approach. So Jim Henson Studios that animates Muppets or designs the animatronics in terms of the workflow and even how they convey emotion and animation through the movements.
Yeah, Jim Henson's like my hero. Yeah, totally. I spent a lot of time looking at like how the Muppets were designed and all that kind of stuff. I mean, I come from mostly a visual arts background, so for me this seemed like the natural way to go about things. And I was actually surprised to see that the engineering approach wasn't more the Muppet approach, because that stuff is brilliant.
Thanks.
All right, let's thank Paul again.